Hello, and thank you for joining our webcast, Optimization of the EV and HEV Powertrain, Robust, Efficient Electrical Machine Design. My name is Lisa Arrigo, your moderator, and I'm with SAE International, the host for today's program. During the next 60 minutes, Dr. Emad Dalala, Application Engineer at ANSYS, and Brian Peasley, Chief Engineer of Propulsion Systems at Magna Electronics, will examine EV and HEV powertrain architectures and the simulation-driven product design process. Dr. Emad Dalala will be our first speaker. He is a specialist in the modeling and simulating of electromagnetic devices and has written extensively about modeling electric machines. Our second speaker, Brian Peasley, directs inverter, motor, and generator design, development, and application support for electric propulsion systems, and delivered the propulsion system for the 2011 Ford Focus EV, as well as other eDrive components to Chrysler, GM, Daimler, Volvo, VW, Fisker, and other non-traditional electric and hybrid vehicle OEMs. Both Emad and Brian will answer questions from the audience during our Q&A in the second half of the program. Please send us questions at any time by using the Ask a Question box on the screen. You may also use the Ask a Question box to alert us to any technical problems you might have. However, if you're having difficulty seeing the presentation, make sure your pop-up blockers are disabled. And now, let's welcome Dr. Emad Dalala, Application Engineer at ANSYS, who will begin our discussion. Hi, Emad. Thanks for being with us today.
Hello, and thank you, Lisa, for your courteous introduction. It's a great pleasure to have you all here today. I'm delighted to discuss with you the state-of-the-art simulation-driven solutions ANSYS provides for the design and process of an EV powertrain. A very warm welcome from me. Thank you, Lisa.
Oh, thanks, Emad. Emad, you've brought with you a poll question for our audience. Let's bring that question up on the screen for everyone to see. The question is, which design challenges are you facing? Please choose one of the following answers. A, core losses. B, demagnetization and temperature dependence. C, cogging torque, forces and torque ripple. D, flux weakening, torque speed curve, and efficiency mapping, or E, all of the above. Please make your selection now. We'll review the results of this audience poll later in the program. And now, Emad, I will turn the webcast over to you.
Thank you, Lisa. Today, Brian and I will go through the recent advances in simulation use for optimization of the EV powertrain electrical machine design. Many of the features I'm presenting today are actually new and included in our latest release, R15, which was just out today, 2 days ago. I'll start with a question to the audience. What is simulation? And I'll answer that. Why do we need simulation? The use of simulation software is actually the science of creating physically accurate numerical models that represent the behavior of real-life systems. In other words, simulation is used to predict a physical behavior without the need for experimentation. In my part today, I'll focus on introducing the ANSYS tools, while Brian will focus on the benefits of these tools, how these tools are applied to accomplish optimal designs for EV, HEV powertrain systems, to reduce costs, and so on. So, let me take you through the simulation products ANSYS offers for the design that you see in this slide now. We offer complete set of simulation engineering tools for different physics domains that interact together in various ways. In this chart, which focuses on electromechanical system simulation tools, we show here analytical tools such as RMExpert, BExpert, which are used to narrow the design space and to create SE-based models. Electromagnetic tools such as Maxwell are specialized in the design of electromechanical devices. We also have mechanical CFD tools. And in addition, recently ANSYS acquired a company for embedded software named Estral, whose main product, SAE, completes our system strategy led by Simplorer, which is in the middle picture. Do these tools interact? You see that these tools talk to each other at different levels. If you can see the lines with different colors show you the type of connections and interactions between these tools, including code simulation, model order reduction, and of course, model generation. In the next slide, I will shift the focus in the electromagnetic design flow of electrical machines. Starting from RM Expert, we can narrow the design of a rotating electrical machine into a limited set. So RM Expert has many templates for electrical machines. In addition, the tool can create an FE-based Maxwell model, as you see in the middle of the picture, with a complete geometry and setup, just ready to run. In Maxwell 2D and/or 3D, a detailed design can be achieved. Many effects such as saturation, hysteresis, eddy current, skewing, rotor motion, cogging torque, and bulk magnetic forces, etc., can all be simulated accurately by these tools. Can Maxwell 2D or 3D also import external geometry and operate independently of RM Expert? The answer is yes. Furthermore, if you look at the right side of the picture, we present the electrical machine design toolkit, which is specialized for generating performance curves and maps. These toolkits can utilize our parametric and HPC technologies and can save you significant time creating results automatically and provide you with time to focus on engineering and innovation aspects. Now, we will look into some very challenging modeling problems that are critical for an efficient and robust design of electrical machines. For example, eddy current losses and proximity effect in solid windings or permanent magnets. Just an example. These phenomena are important because they can impact the motor efficiency, performance, and thermal design. Demagnetization, for example, is a key issue that can occur due to loss of heat and can cause disruption to electrical motor and thus the powertrain. We will shortly talk about demagnetization in more detail in the next slides. But before we do that, let's discuss another challenging problem, usually hotly debated, which is the core loss in steel lamination. Commonly, the three-component formula based on loss separation theories of perpetuity is used for modeling core loss. But many engineers and scientists found some limitations in this formula, including effects of minor loops, scan depth, mechanical stress, etc. So ANSYS has introduced in R15 a vector hysteresis model for the accurate modeling of minor loops. Can the user conveniently enter own core loss formula he or she likes? Yes, as we see on the lower bottom picture, we have recently developed an environment for user-defined core loss modeling, where the user can enter his own equation in a sample template like we show on the screen. Now, earlier I underlined the importance of modeling demagnetization inside permanent magnets and the consequences of that. In Maxwell, we developed a dynamic demagnetization model to study the effect of loading, short circuit, etc. Moreover, the effect of temperature can be modeled by setting the object temperature or by coupling Maxwell with a Fluent, which is a CFD tool that calculates temperature distribution. This slide shows ANSYS Workbench, which is a capability or an environment developed to couple multiphysics and domains, as well as mapped solutions results from different solvers, such as electromagnetic, CFD, thermal, and structural mechanics. In this picture, losses are mapped from Maxwell into Fluent and forces from Maxwell into structural mechanical. Fluent solution is also mapped into structural to study further phenomena such as deformation noise, NVH, and so on. In the beginning of the presentation, I highlighted and showed Simplorer as the core tool for system-level simulation. Here is an example where Maxwell is coupled with Simplorer in transient-transient co-simulation, where the whole electrical drive is integrated, including detailed modeling for power electronics such as IGBTs.
Another common approach is to import a reduced order model, as we see in the right-hand side, in the right side of the picture. The idea is to import a reduced order model from Maxwell based on GQ theory for dynamic behavior and simulation of control schemes. Now, I also earlier mentioned that key part of simulation is the automation flow and design process. Recently, we developed a customized electrical machine design toolkit to generate efficiency maps and performance curves automatically. Among many other performance maps, total loss, separation of losses into winding loss, coil loss, magnetic eddy current loss, and of course efficiency maps. These losses are virtually impossible to separate by measurements, so simulation provides a great way to design your motor with greater accuracy and detail. Efficiency map, of course, can be generated, and it is vital for an HEV drive. The designer of the motor wants to know which regime in the torque speed regime is giving optimal efficiency and so on. Guess how many weeks with the measurement of such a map can take? It can take up to 4 weeks or more, while only a few hours by simulation. My conclusion is ANSYS offers the best-in-class tools for simulating and optimizing EVHEV powertrain systems, and the tools can produce a robust, efficient electrical machine design. We offer a complete suite of tools that interactively exchange data in one-way or two-way coupling directions, as seen in this chart, with temperature feedbacks, etc. Now, the question I'd like to ask the audience: when would you use simulation software? How is it used? When do we need it? Here's my take on this. Whenever processes involve variability, multi-physics, and interaction complexity, simulation is really important. It can give you lots of advantages. A powertrain or electrical drive is a very complex system that requires simulation to achieve optimal and cost-effective design. Other design techniques, such as spreadsheet and flow diagrams, often ignore or treat these complexities as averages, with important consequences. Benefits of simulations: in brief, I say, to simulate physical phenomena that are impossible to measure, speed up design cycles, and save cost. Shortly, Brian will elaborate on the benefits of simulation tools. Now, I would like to thank you all for listening, and I will go back to the moderator, Lisa, so she can view the results of the poll question. Thank you.
Thanks, Imad. Yes, the results of the audience poll should now be on everyone's screen. The question was, which design challenges are you facing? And the majority of the audience selected E, all of the above, over half. And then we had about 10% choosing core losses, 10 the magnetization and temperature dependence, a little bit more for cogging torque forces and torque ripple, and flux weakening, torque speed curve, and efficiency mapping. So, interesting results. What do you think of those, Imad?
So, I can agree that core losses are a key component of the design, especially for electrical drives, where we have a variable speed. The higher the speed, the higher the losses, and they can be significant. Demagnetization can affect the performance of the motor. The motor can fail if the magnet falls to demagnetization. So modeling, predicting the behavior of that is key. The torque speed curve efficiency mapping, as I mentioned, from efficiency perspective and from capability perspective from the motor, for the motor or generator, are also key, and the designer of the motor wants to know in advance how these curves are. Thank you.
Thanks, Imad. And now let's bring up on screen the second and final audience poll. The question is, which aspect of motor design do you seek to improve? Please choose one of the following answers. A, reducing engineering time and cost of materials. B, increasing the efficiency of the motor and inverter. C, cooling and thermal effects. D, structural and NVH. E, system level strategy. Or F, all of the above. Please make your selection now. We'll review the results. review the results a little later. And now, it is my great pleasure to introduce our next speaker, Brian Peasley, the Chief Engineer of Propulsion Systems at Magna Electronics. Hi, Brian. Thanks for joining us today.
Well, hi, Lisa. Thank you for the kind introduction. And I'd like to thank SAE for the opportunity to share Magna's capabilities in motor optimization for the EV and HEV powertrain using the ANSYS multiphysics tools. When Emad talked about how the technology has changed, I can tell you that in my last 20 years, starting in the release of the Ford EcoStar and Ford Electric Ranger BEV, today's Ford Focus BEV is quite a bit different than those. Motors certainly have become smaller, lighter, and more efficient, and with more complex controls for today's permanent magnet machines. Basically, we've doubled the power density while improving the overall e-drive efficiency by more than 10%. Together with other vehicle technologies, particularly in the battery technologies, the practical range of EVs has also doubled in this time. And I'll show you how we went about doing some of that in increasing the range and performance. So what's your motivation as a e-drive design organization? You want to contribute to delivering the best-in-class performance. And the way we measure that, typically in a lot of cases, what drives purchasing decisions is that window sticker. And what the customer sees is a range and an efficiency in terms of a watt-hour per mile basis. And as you can see, there were a few vehicles launched in 2012, one of which was the Ford Focus battery EV, among others. And which do you think had the best watt-hour per mile efficiency? And how did we get there? It may surprise you to find out that the Ford Focus BEV had a 320 watt-hour per mile drive efficiency, which put it best in class at the time of its launch. And the way we did that was understanding trade-offs and using the modeling tools, particularly some from ANSYS that we'll go over today, in optimizing the electric drive. So I can't say we can't take credit for everything. Of course, it takes a lot of work at a vehicle engineering level to achieve best-in-class efficiency. There's a lot of other vehicle dynamics that contribute to the overall watt-hour per mile rating, and it takes all those disciplines of engineering working together to improve the overall vehicle dynamics, drive efficiency, and performance. I'll talk about essentially how we went through that and the focus areas of the motor power electronics. So, when we started out, we were nowhere near being that best in class, and we needed to get 10 more miles of range. So we had some brainstorming, and we looked at aerodynamics and drag coefficients and what we thought, with all of the options available to us, where we could get an increase in range. Mass reductions was also looked at. Auxiliary losses, which can be an interesting discussion and understanding of HVAC, and those big woofers people like to put in, they take energy too. There's also a large contribution in friction in the driveline. When you have a simpler drive system with lower friction components, each one can have a fairly large percentage contribution. What I'm going to talk about today, of course, is the inverter and motor and how we made some changes and understood the design and got to a design with incorporating some ideas in optimization of the motor. So the first thing, when you start out in a program like this, you have to understand what your requirements are and what you have to meet. And we did that. We re-reviewed this in order to close that gap in mileage. First step is looking at what's required. You have to meet not only 0 to 60 types of performance, but 30% grade, which tends to define this peak torque capability in the first blue line at the top. And additionally, in terms of meeting grade, you also have to meet cruising requirements, which you see these lines here are basically sustained cruising at a highway speed at a given 0 grade or at a higher grade, and these determine some continuous operating points and total power requirements during cruising. So these are some of the critical points that define that, and then there's a lot of iterative vehicle modeling going on to make sure we're meeting those requirements. So the next thing is, once we've defined that operating envelope of the machine, is to look at what type, what motor topology, and there's a sundry numbers of machines that have been available in the industry for many years. And they all have their benefits, and based on the usage profiles, their place in the market. You can look at these machines, and what we focused in on in our area was looking at different topologies between switch reluctance, asynchronous induction machines, permanent magnet machines, considered some separately excited machines, and looked at where they were. Ultimately, based on our performance profile and packaging and time to market, we did ultimately select the permanent magnet machine. But we did do some detailed attribute trade-offs, and we looked at keeping the inverter constant, looking at the constraints of the battery and packaging, keeping the motor OD constrained and the length constrained, and did multiple ANSYS 2D simulations and looked at the alternatives and what it gave us in terms of peak power and torque, resultant inverter phase current, and could we still achieve the performance at low battery state of charge? When you get down to 250 volts, 240 volts, can you still meet the performance requirements of the application? And you don't want your vehicle to have different performance characteristics as the battery changes state of charge or aging or temperature. So that was an important aspect to keep. And also, of course, you have to look at cost, and one of the ways in a motor design to quickly get an idea of cost is looking at mass. It impacts vehicle range, it impacts cost. So that's another attribute. You can extract information from your ANSYS modeling tools and understand mass and size implications for the various topologies. So the next point, once you've got your motor selected, in our case, in an overall electromagnetic geometry, is to look at how to minimize loss or maximize efficiency, and looking at the operating points and what elements of the electromagnetic design affect those operating points. This is an illustrative graphic here that shows in that high torque region, copper losses tend to dominate. In applications where you spend a lot of time in that region, you'll see unique applications of wire or bar geometries in order to get that resistance very low. Alternatively, potentially another extreme case, you may be spending all your time cruising at high speed, or a majority of your time cruising at high speeds, and all of these high frequency effects in core losses become very critical. You may also be a performance car where you want to have good highway performance over a long cruising range, and this continuous power range with the arrows moving up with the goal to increase that cruising capability with high continuous power requirements drives another aspect of trade-off and analysis around heat transfer. Is that curve is largely dependent on that element of the thermal management, which the tool does give you that ability to understand as well. Now, after we understand the elements of loss, so that gives us a picture. So what we did in that case was to take the motor operating envelope shown on the left and the resultant efficiency map that we got from the modeling tools, plot that in a contour plot, use another tool to model the vehicle, and equate that to the efficiency operating point in the map. So you'll see all these scatter points here. These are basically all of the operating points in the EPA urban dynamometer driving schedule, the UDDS schedule. And so we look for clusters of operation. We map those over to a operating point of efficiency curves in the machine, and understood that if we're having these large clusters of operation here and these low lower speed points, lower torque points, some of the loss components of the electromagnetic steel may be critically important. So again, another way to look at this too, when you're looking at your topology trade-off, you can do a similar approach. This is just, I took an example that was shown at the 2011 SAE Electric Powertrain Motor Symposium, where Mr. Bolton from REMI did a study of interior permanent magnet induction machines with aluminum squirrel cage rotors and copper squirrel cage rotors, and looked at the operating efficiencies in a contour map. And I did sort of a similar thing. I take our operating points and map those, and you can see where we have these large clusters of operating points. It does fit right into that sweet spot of the interior permanent magnet. So it's another way to look at what you're doing and understanding you've made a good selection in your motor topology. So going on from that, now that you have a permanent magnet machine, just what sort of magnet are you going to use? And the magnets of choice these days are rare earth magnets, and people always tend to ask the question, why? Why a rare earth magnet? They're so expensive, etc. And there's a lot of elements to that. I mean, cost is one element, performance, of course, but a good illustrative point that my colleague Steve Constantinitis, the Director of Technology at Arnold Magnetics, likes to show in all of his presentations is this chart that shows the relative magnet sizes. And you can see from an Alnico magnet down to the neodymiums, the huge benefit you have in terms of size relative to strength. And that benefit in a vehicle design, many times when you do the system trade-off with efficiency and size and weight benefits, the cost of adding battery to make up for mass and efficiency losses more than pays for itself in the magnet arena. The second element of efficiency to look at is sometimes taken for granted a little bit, is the electrical lamination steel, the non-grain oriented electrical steels. And the key to understanding this, and different than typical industrial design, you look at these curves, hysteresis curves, as you increase the operating frequency, fundamental frequency of the electric machine. You can see how they get bigger. You integrate those areas, and you end up with the loss figures for that steel. And you get tables like this from your manufacturer. Typically in industrial designs, you have focuses around 50 and 60 hertz. But I can tell you in electric vehicle design, you look at what drives the fundamental frequency, these rotational speeds, the number of poles in your machine primarily, and then ultimately tying that back to your vehicle design. You tie that to your pole pair count, your gear ratio, tire size, and you can translate the vehicle speed into an electrical frequency in the machine. And you're no longer looking at the typical 50, 60 hertz kind of lamination material that's suitable. When you look at this table, you see something around 50, 60 hertz is in the 5 mile an hour operating range, and it's not a very useful point, not a frequent operating point in the vehicle. So quickly you can see that it's really a different machine design problem you're looking at here. So finally, there's still other aspects of the design that have to be addressed in addition to the materials. So the key materials in magnets are the copper wire, and that we talked about, the copper fill factor and lower resistance. Ultimately, all of that has to feed into a efficient motor control scheme as well, because without having this, the benefits of a good motor design may not be achieved. So just to go over this quickly and to provide another benefit of what these modeling tools do provide for you, essentially what happens, the customer is going to step on the accelerator pedal, and a vehicle torque arbitrator, a vehicle controller, will send a torque request to the inverter, and that's shown in the upper left-hand corner, T_REQ. And that is processed in the motor control to translate that request into components of the electrical current to produce torque and magnetic field, the so-called ID and IQ. And in this table, an accurate model is needed, and one of the things that the tool can provide for you is an export of these flux tables as a first starting point in your optimization of the control and understanding of the control. So that can be a direct export out of the modeling tools. Other aspects of the motor control are implemented, and with all of the proper control and calculation of the phase advance angles and the quadrature transformation and the Clark and Park transformations, the inverter is able to provide an accurate VD and VQ transformation into a voltage PWM that's applied to the motor through the power transistors. So then there's proper feedback, and all of that works in a standard control model. And then additionally, as you get that feedback back, the torque estimation block is another key element that can be enhanced by using some of the FEA tools to build an accurate torque estimation model that is then fed back to the vehicle. So that's another important aspect not to be overlooked in the motor design. So when looking at this, there's various aspects and physical limitations electrically primarily that you're faced with, in this case in the motor control, and commonly referred to as a maximum torque per amp methodology can be shown in a diagram such as this, with your D-axis and the X-axis is your flux component, and the Y-axis is in your Q torque producing component. You can produce contours of torque and a circle of maximum current available from the inverter, and then there is a dynamic ellipse, if you will, that is a resultant of your battery voltage or other DC power source, and that size is a bit dynamic and varies in proportion to that voltage. So that's sort of what drives the importance of having that good motor model developed from your FEA to have a good ID/IQ lookup, so that you could travel along these maximum torque per amp or maximum efficiency points. So, and then that Imax can also be a bit dynamic as well, because there are thermal limitations in the inverter or other events that need, in terms of battery capabilities, that may limit that Imax point. So this looks static, but it's actually a very dynamic picture that needs to be properly modeled. And then once you do all that, you're going to do some testing. You're going to take your first attempt at getting the maximum efficiency. Is that always based on a maximum torque per amp, or is there another way to do this? And so this slide just shows you an overlay of we did testing, and we developed a red curve that gave us a maximum efficiency curve, and then the other blue curve is essentially your maximum torque per amp. So you wanted to make a torque command of 125 Newton meters. Where do you select your advanced angle? Do you select it for a maximum torque per amp, or do you map it to the maximum efficiency? So these are things you can do in that lookup table feature to ultimately further optimize and improve your vehicle range. So I'm going to look at a couple of other project examples of where we use the modeling tools in slightly different applications. So that was a long story about getting to improved range in the battery electric vehicle application. There's many other aspects of the design tool that can be done. The first project I'm going to look at is a optimization of a electric machine that was for a generator application, and was a little bit smaller power than what you would expect in a traction, and had different operating parameters. So this is a brief description of that machine and its requirements. So what we did, of course, you start out, you have objectives, and you can use the FEA optimization method to look at optimization in terms of mass, which, as we talked about before, equals cost in many cases. And then also reducing the magnet size is an important aspect of maintaining a good cost position. Improving your efficiency and understanding your trade-offs in efficiency, and more often than not in these applications, the vehicles are very quiet because you don't have this icy engine thumbing away in the background, and you can hear every noise. So torque ripple and resulting forcing functions from the machine are important to understand in terms of bringing the noise vibration harshness, or NVH, of the torque ripple component to a good understanding when you're trading off the designs. So we set out and we did experimental versus testing. So this is essentially looks similar to what you've seen before, slightly different curve, of course. That was ultimately the test result. But we had, of course, first we did the 2D simulation, and then we looked at the results and got a very good correlation, if you will, from the test results to the 2D simulation. It always is a kind of the key barometer. Everyone wants to see these maps, and it's also, as Emad referred to earlier, having the accuracy built into these tools provides much better than in the past in terms of their accuracy in modeling and understanding the split between core, iron, and other losses in the machine. So we were, at this point, we're trying to do a major material cost optimization, and in looking at the, the machines are, when you look at them, they look fairly simple, and really they have major cost elements of the electrical steel, the copper wire, which copper has become an expensive commodity these days, the magnets, which have gone up and are coming back down in terms of their cost, but they're still the most expensive by far by mass. So the idea was, what can we do to reduce the magnet size to further enable cost reduction in this design? So there are tools available in the ANSYS tools that allow you to do some of this parametric iteration. Our goal was to reduce it by 20%, and so there were some optimizations run using parametric analysis to get us where we needed to go, and there were things done with the angle of the magnets in the V and size of the magnet, while still maintaining requirements to the inverter for the same voltage and current. And we were able to achieve that. We did, of course, have effects in efficiency, and you can see in some cases were better, some cases were worse, and ultimately what this comes down to as well, as shown before, you have to map your operating points in there to understand what is the real effect of that in the overall vehicle application. So that also modeled then was looking at what is the resultant to that NVH, what is the torque ripple, and in this case, because this is in a generator application, we accepted some areas of higher torque because it's not felt as much to the drivetrain when it's not in a traction application. So that was a trade-off you make. You get a smaller magnet, a lower cost, slightly increased in some cases, and where your area of interest, you keep it quiet. So that was, it's a key element to understand and easily modeled with the multi-physics tools. And I know this is this is those of us in the management of engineering. We're always struggling with the time constraints, and of course our suppliers understand that as well, and our tool suppliers certainly as well, that you have to maintain those constraints. There is an ability to improve the time it takes to do all this work. It used to be very computation intensive, and fortunately we have these tools that are have a very high computational ability, and if you need to increase that, there's an option where you can put additional computation time online in these distributed solvers solutions, which provides a benefit in terms of the time it takes to do all these trade-offs and analysis. So that was what enabled us to look at a reduction in the overall magnet size, geometry, and ultimate cost of that application, and understand all of those effects. We had I have a second project that I'll talk about that was done by our office in Austria. This is an application that's in production as a plug-in hybrid electric vehicle and sold by Volvo. but it's an application slightly different, being essentially launch capable and parallel hybrid. You'll see that it's much smaller in power than our typical battery electric vehicles at 50 kilowatt with a 20 kilowatt continuous. Lower peak torques, 50 newton meters less in peak torque. I had some unique attributes here to be able to do that in that application. Particularly, was a very tight package. Anytime you reduce the package space and increase this power density to the point we had to fit it into an existing platform, your heat management becomes of paramount importance. So what I'm going to share, of course, we went through the same, any design process follows similar as what I've been through before, but in this case, I'm going to show you some of the benefits of a multiphysics tool that EVHEV talked about in terms of sharing design information between the elements of your multiphysics modeling tool. So we did all that electromagnetic sizing same as before in a typical design, and there's lots of elements. I talked about just sort of the small key elements of cost, but there's a lot of other ingredients that go into a motor that you have to have for electrical isolation. And anytime you put in an electrical isolator, it also tends to be a thermal insulator. So there, you can see in the top right hand these coil separators. It's a Nomex Mylar Nomex that is not a terribly good heat conductor, but so very important to model this and to be able to understand the effects of that separator in your thermal model. The head windings, of course, with the copper losses, and all the lamination iron and the geometries of that. It all can be ported in and then modeled in a similar environment. So of course, similarly, you do that for your rotor, and you can take that same CAD data you have from your design and bring it into the ANSYS tools and perform your rotor model generation and do the same thermal analysis there. Ultimately, these are very complicated models, and we're talking about a huge number of nodes, millions of elements, and lots of cuts to look at where your heat is being concentrated and where you can affect a better thermal interface. The results, essentially, from as EVHEV talked about, you can do lumped model where you lump all your losses in these larger elements and see how that run it like that in a typical tool, or you can map the losses into a finer mesh as done here. And what you can see is it can be dramatic. You can see 10 to 15 degrees of temperature difference in the model that you don't get surprised when you get into test, potentially, in this case. So now that's the real benefit, the accuracy of modeling, and not missing something important and getting the test, finding a heat, you have high heat, and going back and redesign. That's very expensive. So it's important to understand these aspects of design up front, not just from an electromagnetic perspective, but when you get into high power applications and high power density, particularly, thermal is the key factor. And the same was done in the rotor, of course, and these rare earth magnets are very critical in terms of if you get them too hot, they lose their permanent magnet strength in some cases. So it's very important to understand that, and you can see a lumped versus mapped approach gives you differences that could be very important if you're close to the limit of your design and optimization, which typically is required in these applications. You don't have a lot of extra headroom given to you in these applications. So that concludes our sort of three examples of where we used the three-dimensional multi-physics modeling capabilities. We use more than just, you saw a lot of Maxwell 3D and CFD. There's other benefits that we, in the Simplorer region, we use these in our inverter design and bus bar. The Q3D, we can model all our bus bars, EMC filters, and so forth. So there's a lot of benefits. These are benefits specifically maybe for the motor design aspects. So one of the benefits, of course, you have a visualization, and then ultimately all of us engineers tend to be somewhat visual in our understanding of the physics, and it's nice to have that visual because magnetic flux and heat flux are just hard to see. we're always looking to reduce the time to market, and by reducing prototype phases, it reduces time and it also saves costs. So you get it right quicker when you have a good design that's accurate in modeling up front. Additionally, as I talked about, ultimately you have to control this machine. Software controls are just a huge element of today's electric drive. And to have an accurate motor model saves a significant amount of time in that coding process for your motor controls. So ultimately, it gives you shorter time in the development from concept and gives you that higher confidence once you get prototype built and get it in the vehicle. You're going to have a better result. So ultimately, it comes down to the key benefit, as I'm told by some of my OEM customers, there's only 3 things important in the motor design, and that's cost, cost, and cost. So here, the bottom line is cost reduction is heavily enabled through optimization and using these kind of tools to reduce your cost and be successful. So at this point, that concludes what I have today. It was my pleasure to go through this with you, and I'd like to turn it back to Lisa for the results from our survey questions.
Thanks, Brian. Thanks for that wonderful presentation. Yes, let's bring up on screen now the results of our second audience poll. To refresh everyone's memory, the question was, which aspect of motor design do you seek to improve? And we'll bring the results up on screen, and the majority of our audience, well, the majority selected all of the above. But of the various choices, B, increasing the efficiency of the motor and inverter, had the most results other than all of the above. At about a third of our audience selected increasing the efficiency of the motor and inverter. 18% cooling and thermal effects, about 7% reducing engineering time and cost of materials, and then 5% at system level strategy, and about 3% at structural and NVH. Interesting. Brian, would you like to comment on those results?
Well, I tell you, that's you can tell some people out there that have been through this before, because ultimately when you put your design out there, one of the first things they do want to see is that efficiency, and it's important. It reduces your cost to the vehicle system in terms of your battery costs, and having a good thermal in these aspects, whether it's in a transmission or whether it's a separate electric machine. There's some tough environments in the automotive you have to live with, so understanding the thermals. So I think the results are very indicative of what you see in the real world, and because there's so many in the all the above category, ultimately, as people understand, you can't focus just on one element and ignoring the other and be successful. So it's very good information.
Thanks, Brian. It's now time to start our audience Q&A. Audience members may send us a question by using the Ask a Question box on the screen. And let's see what our first question will be. Oh, here's a good one. I have noticed with the 2013 Leaf and Volt, efficiency has been gained versus the 2011 model years, maybe 10% more at most. How much more efficiency can we get from revised motors, power controllers, and battery chargers? Great question to start our Q&A. Emad, do you want to answer that question for us?
Yes, I can comment on that, and probably Brian can also a little bit give some insight about it. So revising the motors, there are lots of detailed optimization that could be simulated and improved in advance before prototyping, and parametric analysis. Right now, the tools that we have, for instance, the electrical machine design toolkit that we provided in ANSYS, can provide you a way to compute the efficiency in a very quick manner and change the voltage, the battery level, and see what's how your efficiency of the motor, and you can make parametric sweeps for certain small details. For instance, in a motor like a permanent magnet molds, the thickness of the bridge between the magnets and the rotor, and all these few details can, and of course the materials properties. If it's a steel laminations with different thickness, it can affect your speed efficiency at higher speeds and so on. So yes, Brian, would you have some more?
Yeah, no, I can tell you essentially, and you'll see as each model is refreshed, and you'll see improvements. And a lot of times, what's been remarkable is, like I talked about, the materials that go into these machines aren't your garden variety industrial materials. Been a lot of work in particularly, we're seeing results in the steels and magnets, particularly that result in better efficiency performance through the material science, lower losses and laminations, and better performing magnets in terms of graded magnets, in terms of how they, maybe not necessarily a fully uniform mixture in the magnets. There's some optimization in the grading. There's, like you talked about, these thinner laminations, and we did go to that, and we were able to use the tools to accurately model using that user-defined curves and understand those. But I think I'd say in the motor, probably in the 5% range typically you can achieve. The rest of these big gains I think you see are results in battery improvements, battery controls, mass reductions, and aerodynamics. I know when you look at some of the newer vehicles when they come out now, they have active air dams and other features, and the batteries I think still are providing a great amount of some of these improvements year over year.
Very good. The next question is for you, Brian. How are the efficiency maps validated?
So you saw a little bit of a picture in one of the slides. You could see the picture of the motor installed in a fixture. That fixture is inside of a dyno cell, so we were able to fully instrument the motor from AC electrical power in, measuring phase currents and phase voltage. We use an accurate power meter in that case, an electrical power meter. The output of the motor is in a mechanical shaft where we have a series speed sensor and torque transducer from which we can calculate the mechanical power. And we have do a lot of gauge repeatability and accuracy testing to understand capability of those measurement systems, and then we run the motor. This is the things that Imad talked about. It take weeks to do in the lab, is to run all those torque speed efficiency points at various temperatures and actually measure that efficiency point from electrical power in and mechanical power out, and compute the efficiency and compare it to the map. So that's what we do, and it can be a month-long process between optimizing your measurement system, getting all your changing torque transducers as needed to get the most accurate results at the various torque levels and speed levels. So that's how it's done. It's done by measurement in a dynamometer laboratory. Very
good. Thank you, Brian. Imad, you have the next question. One of our audience members writes in a question about demagnetization. They want to know if you can provide any detailed tutorials about it.
Yes, so we'll follow up with you later on, and we'll send you the tutorials. Yes, we have plenty of examples and tutorials detailing the use and accuracy, and we have also some scientific papers published in the literature.
Very good. All right.
We'll follow up.
The next question is also for you, Imad. How long does it take to generate optimization tables for IDIQ?
It will depend. If you're using 2D, which is a common way, it can take an hour or half an hour, so it doesn't take a lot. If we utilize our DSO, which is technology for our HPC to distribute the different parametric analysis into multiple cores, then we can reduce the time significantly into even a few minutes. So it can vary from a few minutes to 1-2 hours.
Thank you. Here's an interesting question. This is for you, Brian. How does a motor controller adapt to increased internal resistance that occurs in older battery packs as they age?
Okay, so that's a very good question, because it's an important requirement in these designs to be able to have consistent vehicle performance over the state of charge and age of the vehicle. So essentially what you have to some degree is at the beginning of life, the battery may have a little more capacity, a little more voltage than you utilize, and as it ages, it comes down, but you've accounted for that aging in your worst case design point. You actually designed to operate down at its end of life point at lowest state of charge, and that dynamic modeling in the motor control with that voltage ellipse. So as the battery ages, that constraint is dynamically modeled by measuring the battery voltage directly, and then we also have a battery controller in the battery pack that sends information directly to the motor controller on the state of health of the battery and just how much regeneration current and how much traction current is available to use. So bottom line is we understand the aging effects of the battery up front, and that's what defines some of the minimum voltage operating points and minimum current that we can get out of the battery, and that's one of our design constraints, and then the controls adapt for it over the age.
Thanks, Brian. You also have the next question. An audience member wants to know, why don't you use three-phase induction motors? Or were they considered? In some applications, they have much higher efficiency than permanent magnet motors. Brian?
Oh, I love that question. That's an excellent question, because that is the first thing you have, one of the first things that you saw in the beginning. So there are, if you look in the exactly as the person who submitted that question said, there are areas where the induction machine is more efficient. You can see that in the modeling. That's where it becomes important to understand your usage profile. Can you take the extra package size? Can you provide the extra current that's required for an induction machine to operate it in the region where it does give you that benefit? So I'll tell you, there are electric vehicles on the market today. The Tesla is one example, for instance, who has a copper squirrel cage induction machine, and because that vehicle has a high capacity battery, it makes up for potential losses of efficiency, but that operating point and high speed gives them a performance that they're looking for. So there's not any one right or wrong motor topology in these applications. What the right thing you have to do is do the modeling up front, understand your drive cycles, and make a selection of the motor topology that matches the application. You'll see the same thing with a start-stop application versus a battery electric. So in a hybrid application, which I spent most of my time talking about more like a battery electric, but in these prevailing technologies today in the start-stop systems, you're spending all this time in that peak torque region, and in that case, you may see benefits of an induction machine there as well. So I think there's no one right answer in that case. It all comes down to applying the proper application of motor technology to the drive cycle.
Thanks, Brian. Our next question is for EMAD. This involves core loss computation with ANSYS Maxwell. The audience member wants to know, how accurate is this, and has this been validated with experimental results? EMAD?
Yes, so Maxwell has, we have the three-formula core loss model, which is based on the separation of losses by 2G theory. This theory has been validated in a lot of applications in literature. We have, through probably the results that Brian showed for the efficiency map, that show that the model is pretty close to reality. There could be some deviation at higher speed. But on the other hand, ANSYS provided an R15 vector hysteresis model that in the future will be used for core loss computation for the hysteresis, which improves the minor loss modeling. Plus, we also added an environment where a user could, for any type of special material which requires special care for core loss modeling, the user can enter or use his own or her own CoLOS model. So the model, as I mentioned, being validated by several customers and several papers in the literature. I can follow up with that for further details.
Thanks, Imad. And with that, we're at the end of our webcast. I want to thank our speakers for their excellent presentations today and for answering the questions from our audience. I also want to thank Imad and Brian for agreeing to email those audience members whose questions we did not have time to answer. Answers to your questions will be sent to you over the next several days. A survey will pop up on everyone's screen at the conclusion of our webcast. Please tell us what you thought of our program by answering its 3 short questions. This webcast will be archived and available for viewing on the SAE website. An email will be sent to everyone who registered for today's program as soon as the archive is ready. And that same email will include a link to a PDF of the PowerPoint slides, which you can then download. I'm Lisa Arrigo with SAE International. Thanks for joining us.